So we moved on to part C of our ramp problem, and part C tells us that our ramp now has a 5-meter height, and the box starting from the top of the ramp slides down the ramp, and what we want to know is its final velocity at the bottom of the ramp. So the very first thing we're going to do is we are going to find the length of this ramp because we know the height and we have the angle of the ramp. So we want to find this distance that our box is going to travel. So of course we know the opposite side of the triangle. We want the hypotenuse. We are going to use the sine of our angle. 20 degrees is equal to 5 meters over our length. You multiply length on both sides, divide by sine of 20 on both sides. We get that our length is equal to 5 divided by sine of 20. And we just calculate this real quick and get that the length of our ramp is equal to 14.62 meters. So what we want now is to find our final velocity at the end of the ramp after we've traversed these 14.62 meters. And how we're going to do that is we are going to use an equation which is one of a group of equations called the kinematic equations, which we're actually going to explore more in depth in the next set of videos. In the next problem that's posted. So this one equation that we're going to use looks like this. Our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our distance. And we just now got our distance, our 14.62 meters. We know our initial velocity at the top of the ramp. The problem said that our box starts from the top at rest. So this is going to equal 0 meters per second. And we do have an acceleration value because by relation, we know that force is equal to mass times acceleration. And in order for this box to move down the ramp, we need to have a force acting on it. And we do. We have gravitational force acting on this box the entire time it's going down the ramp. But as we solved in the first parts of the problem, the force that we know is truly making this box go down the ramp would be the parallel component of force, because the perpendicular component, which points into the ramp, does not cause the box to accelerate. So the acceleration that our box experiences is due to the parallel component of gravitational force. So what we're going to do is we're going to substitute for our acceleration variable in our equation parallel force divided by mass, because when you divide by mass on both sides, you get that acceleration is equal to force divided by mass. So we're just going to substitute force divided by mass for our acceleration. And our new equation now looks like our final velocity squared is equal to, this value is just 0, so we're just going to ignore that. 2 times our parallel force, let's make that a little bit easier to read, parallel force divided by mass times our distance. And all we have to do at this point is just plug in the variables that we know, which is all 3 of these, and we can solve for our final velocity. So let's solve for our final velocity. Our final velocity squared is equal to 2 times, and then, we don't actually have the parallel component of force listed, but I do remember it from the previous parts. our parallel force of gravity was equal to 83.88 newtons. So we can just write that in over here. Sorry about that. So 83.88. Sorry, let's put this in a parenthesis so that we can discern our numbers from each other. And then the mass of our box is 25 kilograms. So divided by 25, and then times distance. And our distance that we traveled was 14.62 meters. And what we're going to do is multiply this out so that our final velocity squared is equal to 98.106. And then all we have to do is square root both of these values, and we get that our final velocity at the end of the ramp is 9.91 meters per second. So after all of that, we have found our final velocity, which concludes our ramp problem.